Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Alright, welcome to Lesson 15, Rotations, Reflections, and Symmetry. Classwork opening exercise says the original triangle labeled A, right here, has been reflected across the first line, the red one, to B, resulting in the image labeled B. Reflect the image across the second line. So let's do that before we read any further. Do you remember how to reflect an image across a line? Well, you have to put the compass point at the vertex, one of the vertices, I should say. And that's right about there. Very hard to do with the mouse. Okay, you want to open it up and check to see that it's going to intersect the blue segment in two places. That's all we need it to do. So I'm going to make it a little bit smaller though. So I cross there, I'm going to cross there. Alright, so that works. So I'm going to draw a circle. Okay, once I do that, that created two intersection points. One right here and one right here. So now I'm going to take my compass point and put it on that intersection point right here. Rotate this. Make sure it's open so that the radius is equal to the intersection point to the vertex of the triangle that we're trying to copy. So that's right about there. I draw a circle. Okay. And then I do the same thing from the other intersection point of that first circle, which is right about here. Draw a circle, and this new point is my reflection point. So I'm going to do that two more times. I'm going to get rid of these circles so it's less confusing. Okay, so now I'm going to put the compass at the vertex that's closest. We'll do this one next. Right about there. Let's change the color back to green. Draw a circle. It intersected the blue line of reflection twice. Bring that over to the intersection point. Okay, let's change the color to red. And then open it so that we have the radius that is from the intersection on the line to the vertex we're copying. So draw a circle from there. Bring it over to the other point of intersection. Make sure it goes right to that point, which it does. Draw a circle. Okay. Now this one, since it was so close, this intersection point here is approximately the same as where this actually starts to touch right there. So I'm going to go with that. See, because when you're really close, it's hard to see where it's intersecting on the other side. All right, get those circles out of the way. We have one more point to do. Put my compass there. Let's change the color back to red. Rotate. Circle's way too small right now. It will never cross. Extend it to make sure it crosses 2 times. Still too short. Get it out like this. And that's too far. And this should be okay. And actually I could use that point of intersection of R right there if I wanted to, but let's avoid that. So let me just change the radius a little bit, like so. Draw a circle. Oh, that's too short. Let me open it up some and draw a circle. There, that's better. So there's our circle, and the intersection point is right here, and the other one is right here. So I put my compass, rotate it so it's on my paper, and put it right at that point of intersection. Okay. open it so that its radius is going to go through by that vertex right there. Move this over to the other point of intersection. Right about there. Circle goes pretty close right there. So my point of reflection would be right here. Now let's get rid of those circles. Okay, and now I'm going to draw segments that connect these two. So I will start here. Let's use segment color black. That's fine. Right here, going to there, to here, to there. So there's our reflection twice of A. The pre-image A was reflected to B, the image. The image B is reflected, is now the pre-image to this new one that we can call C. So if I call that C. So what they're saying now is Carlos looks at all the image, looks at the image of reflection across the second line, okay, this one here, and said that is not the image of triangle A after two reflections, that's the image of triangle A after a rotation. So is he right or is he wrong? That's the question. So what I'm going to do is I'm going to draw a triangle. I'm going to trace triangle A electronically. Okay. Okay, so I spared you the time here. So where would our line or point of reflection be is the question. So what he's saying is that's not a rotation, or it's not a reflection twice, it's a rotation. Well, if I rotated this around 180 degrees, would that end up on C? Okay, so I've reconstructed this in Geogebra, okay, geogebra.org calculator, and so what I've done is I've taken the image from here and I copied it over to Geogebra here, and the point of rotation, if this is true, should be where the two lines of transformation are. So I'm going to rotate each side of this triangle about the center point here, and I did some calculations and it comes out to be about 215 degrees, give or take. And when I do that, I'm really close to my new location. Now if I keep doing that for each piece, 215 degrees. Okay, here's A, B prime, and then this side, 215 degrees. Oh, I didn't do this side yet. My fault. This one, 215. Whoops, I chose the whole thing that time. That's because this is sitting here, so let me try that again. So I want to rotate AB about C 215 degrees. And that's right here. So I've got this one, I've got this one, I just need this one now. And as you can see, this triangle falls pretty much on top of this one here. I might be off by a degree or two of rotation, but you can see that a rotation will land it on top. So getting back to Carlos. He says it's not the image of a triangle after two reflections. That's the image of a triangle A after a rotation. Do you agree? Why or why not? Well, I sort of agree, but I also sort of disagree. I agree that it is a rotation because I just showed it, but I don't agree that it's not an image twice reflected because it is. So if you reflect something twice, it will equal a rotation of a certain degree, and it won't always be 215 or 14 degrees. So when you reflect a figure across a line, the original figure and its image share a line of symmetry, which we have called the line of reflection. When you reflect a figure across a line and then reflect the image across a line that intersects the first line, you find image is a rotation of the original figure. The center of rotation is the point at which the two lines of reflection intersect. The angle of rotation is determined by connecting the center of rotation to a pair of corresponding vertices on the original figure in the final image. The figure above is a 210-degree rotation, and so it says, but with my copying and pasting, I might have lost a few degrees, but they say it's a 210-degree rotation. Exploratory challenge. And do you understand why it's 150 clockwise? Well, 210 plus 150 is 360, so we could go 210 degrees counterclockwise or 150 degrees clockwise. Land on the same location. So exploratory challenge now says line of symmetry of a figure. This is an isosceles triangle. Two sides are marked congruent, making it isosceles. And by definition, that has at least two congruent sides. A line of symmetry of the triangle can be drawn from the top vertex to the midpoint of the base, decomposing the original triangle into two congruent right triangles. This line of symmetry can be thought of as a reflection across itself that takes the isosceles triangle to itself. Every point of the triangle on one side of the line of symmetry has a corresponding point on the triangle on the other side of the line of symmetry, given by reflecting the point across the line. In particular, the line of symmetry is equidistant from all corresponding pairs of points. Another way to think about line of symmetry is that a figure has line symmetry if there exists a line or lines such that the image of the figure when reflected over the line itself, such that the image of the figure when reflected over the line is itself. Does every figure have a line of symmetry? So let me draw this line of symmetry they're talking about here. And I will draw a segment from the vertex down perpendicular. It moved just a little smidgen when I let go. So if I put it right on the vertex right there. So what they're saying is if I pick a point, say it's right here, then it would reflect across and it would have a reflection point on that side right there. Every single point on those segments will reflect over to their side, and same with the base sides as well. And it says, does every figure have a line of symmetry? Okay, here is an example. This is a quadrilateral. No sides are parallel, no sides are congruent. There is no line of symmetry. There is nowhere where I can cut this in half and one side will fold over and land right on top of the other. So not every figure has a line of symmetry. Okay, now we have four shapes here, four polygons. And it says, which of the following have multiple lines of symmetry? Well, if I drew a line vertical like so, that cuts this polygon, this hexagon in half. I could also draw another one like here, and that would cut it in half this way. I could cut it in half this way. I can cut it in half going through the vertices, and I can do that with all the vertices. So look at how many lines of symmetry that hexagon has. This one's off a little bit. There, that's better. So they're all going through the center. So it has multiple lines of symmetry. This one here doesn't have any. If I drew a segment, if I drew a segment here, yeah. Let's try that again. If I drew a segment there, this folded over, this wouldn't reach. I could rotate it maybe. And you just try different things. Is that going to fold properly? No, that's not going to fold across and land right on the other one. Okay, or is it? No. All right, but if I bring this over here, again, multiple lines of symmetry, make that vertical again, put it on the center, there is a line of symmetry. And let's try that again. There's one there. There's one through the vertices. Like so. And one more. Like that. Okay. So there's the answer. Which of the following have multiple lines of symmetry? The hexagon and the rectangle. Okay, it says use your compass and straight edge to draw one line of symmetry on each figure above that has at least one line of symmetry. Then sketch any remaining lines of symmetry that exist. What did you do to justify that the lines you constructed were in fact lines of symmetry? How can you be certain that you have found all of the lines of symmetry? Okay, I'm not going to go through that. That's very time consuming. That's something you can do on your own. I'm going to move on. Rotational symmetry of a figure says a non-trivial rotational symmetry of a figure is a rotation of the plane that maps the figure back to itself such that the rotation is more than 0 degrees but less than 360. 3 of the 4 polygons above have non-trivial rotational symmetry. Can you identify the polygons that does not have the rotational symmetry? So let me get rid of these lines of symmetry. Okay, so rotational symmetry would mean if I took and put a dot in the center and spun that, would I land on top of itself before getting to 360 degrees? And the answer is yes. If I rotate a rectangle 180 degrees, this point would end up here, this point would rotate around to here, and so on, and it would be a 180 degree rotation, and it would land on top of itself. So this one does. So I'm just going to put a check mark next to the ones that have what they call non-trivial. Okay? More than 0 degrees, less than 100, or less than 360. Because everything, if you put a dot in the center and rotated it 360 degrees, of course it's going to end up where it started and be on top of itself. Okay, so can I rotate this less than 360 degrees and have it land on top of itself? And the answer is no. Can I rotate this one less than 360 degrees? And the answer is yes. I could rotate it a number of degrees to get to here. And there are 1, 2, 3, 4, 5, 6 sides to a hexagon. So 360 divided by 6 is 60 degrees. So if I rotate that 60 degrees, it will land on top of itself. Rotated 120 degrees, it will land on top of itself. 180 plus 60, 240, plus 60, 300. So there's 5 rotations I can do before getting back to 360. And then with this one, so this is a yes. This one I can do the same as the rectangle. I can rotate it 180 degrees and land on top of itself. So the polygon that does not have such a symmetry is the right triangle. When we studied rotations 2 lessons ago, we located both a center of rotation and an angle of rotation. Identify the center of rotation in the equilateral triangle ABC below and label it D. Okay, so we're going to find the center. So in order to do that, I need a compass. And I want the compass to draw in red. I'm going to put the compass at A. I'm going to open the compass up so that it is a distance of less than AC, I guess. Let's just see what happens here. Draw a circle. Actually, no, that's not what I want to do. Okay, just to save time, I pause and unpause, and what I had done was drawn a circle centered at A, greater than half of AC, but less than AC, and then did the center at C with the same radius, and now I have 2 points of intersection where I can draw a segment, and I'm going to do the same with another side, so I'll put this on A, draw a circle, put it on B, draw a circle, and now when I draw a line segment, I'm just doing this very quickly without the tools, that intersects the circle intersections that are green, that would be right here. And then if I did one that would intersect the two, where the two circles intersect, the two red circles intersect, that'd be there and there. So you do two perpendicular bisectors of two of the sides. And then when I get rid of all of my circles here, I can now put a dot at the center of this. Get rid of those segments so we can see it. And that is the center of rotation. Two perpendicular bisectors formed by circles that intersect. Okay. That was from lesson, oh, I don't know, 14. Anywho, there it is. So, identify the center of rotation in the equilateral triangle. Did. The simplest method is finding the perpendicular bisector or at least two of the sides. The intersection of these two bisectors gives us a center of rotation. That's what I just did. Hence, the center of rotation of an equilateral triangle is also the circumference of the triangle. In lesson 5 of this module, you also located another special point of concurrency in triangles, the incenter. What do you notice about the incenter and circumcenter in the equilateral triangle? Okay, hopefully you guessed it. They are the same point if the triangle's an equilateral. In any regular polygon, how do you determine the angle of rotation? Use the equilateral triangle above to determine the method for calculating the angle of rotation and try it out on the rectangle, hexagon, and parallelogram above. Okay, so what you do is you take a protractor and you put the protractor's crosshairs at a vertex. Rotate the protractor so that the 180 or the 0 line is right on your segment. So let me just get this just right. So we're right here. And then you rotate it just so it's sitting right there on C. And what you have to do is, let me see, where is it? There it is. So we use this little thingy here. So there's 0 degrees. So if I rotate 60 degrees, I'm at the next. C would be on B if I rotated this from the center 100 or 60 degrees. So this angle measure is 60 degrees. So angle A is 60 degrees. All right, so is that our angle of rotation? That's the question. Okay, so I was just wondering if you would realize that that is not correct, because if I rotated that again, that'd be 180 degrees. And if I rotated, or I'm sorry, 60 degrees, then 120, then 180. Well, that's a same as a flip, and that would not work. So what you want to do is you want to put your protractor on the center here, like so. Rotate it so that your 0 line from your point of rotation over to one of your vertices is right at 0 degrees. Okay, here's 0 degrees. 10, 20, 30, 40, 50, 60 is right here. That is definitely not going to land on top of itself. A would be like right here now. So this segment would go up to here and then down to here. So it's definitely not landing on top of itself. I'd have to go all the way over to here before it would land on C. And I'm off just a little bit, so let me rotate this, because that should be 120 degrees. like so. So it's a rotation of 120 degrees. So you can take a protractor, put it at the center, put this on the 0 line and measure over to the next. So this angle measure is from the center to here, and here is 120 degrees. How else could we do this without a protractor? Okay, well, if this is an equilateral triangle, then this is 60 degrees, and this is 60 degrees, and this is 60 degrees. It's also called an equiangular triangle. Well, if I then drew a line segment from here to my center, and then from my center over to here, I've now created a triangle where two sides are equal, and then you have a third side. So this angle here would end up being, this angle would be cut in half, so this interior angle here would be 30 degrees, this would be 30 degrees. Let me move these out of the way now. The whole thing was 60. So now if I do this, that would make 30 degrees here, and this 30 degrees, which is 60, and therefore this would have to be 120 degrees to make a 180 degree triangle here. And then you'd have 3 of them. So basically what you have to do is, if you have a regular polygon, which means all the sides are congruent, all the angles are congruent, you take the rotation 360 degrees, divide it by the number of sides, and you get your answer. So you say 360 degrees are in a full circle, divide by 3, there are 3 angles in a triangle, and that gives you 120 degrees. If you took 360 degrees and you had a square has 4 90-degree angles, 360 divided by 4 is 90 degrees. A 90-degree rotation of a square would have it land upon itself. So you just take 360, divide by the number of angles, or divide by the number of sides, depending on how you're looking at it, and that will give you the degrees. So a hexagon would be 6-sided figure, so you take 360 divided by 6, and that is 60 degrees. A parallelogram is a 4-sided figure, and we already did that. That'd be a 90-degree rotation. But a parallelogram that is not regular, it'd be 2 90-degree rotations, and that'd be 180 degrees. Okay, page 3 is pretty wordy. I'm going to try to just zip through this real quickly. Identity symmetry. A symmetry of a figure is a basic rigid motion that maps the figure back onto itself. There's a special transformation that trivially maps any figure in the plane back to itself, called the identity transformation. This transformation, like the function f defined on the real number line by the equation f of x equals x, maps each point in the plane back to the same point, in the same way that f maps 3 to 3, pi to pi, and so forth. It may seem strange to discuss the do-nothing identity symmetry, the symmetry of a figure under the identity transformation, but it is actually quite useful when listing all of the symmetries of a figure. Let us look at an example to see why. The equilateral triangle ABC on the previous page has 2 non-trivial rotations about its circumcenter D, a rotation by 120 and a rotation by 240, as I stated on the last page. Notice that performing 2 120-degree rotations back to back is the same as performing one 240-degree rotation. We can write these 2 back-to-back rotations explicitly as follows. First, rotate the triangle by 120 degrees about D, which would be R sub D 120, triangle ABC. Next, rotate the image of the first rotation by 120. So rotate about D 120 degrees, the rotated figure that was rotated D, or about D 120 degrees ABC already, is what that means. Rotate ABC 120 degrees twice around D is all that means. Rotating triangle ABC by 120 twice in a row is the same as rotating triangle ABC once by 120 plus 120, which equals 240. Hence, rotating by 120 degrees twice is equivalent to 1 rotation by 240 degrees. So rotate about D 120, the triangle ABC that was already rotated 120 degrees around D, is triangle ABC rotated around D, 240 degrees. In later lessons, we say that this can be written compactly as R D120 times RD120 equals RD240. What if we rotated by 120 one more time? That is, what if we rotated triangle ABC by 120 3 times in a row? That would be equivalent to rotating triangle ABC once by 120 plus 120 plus 120, or 360 degrees. But a rotation by 360 degrees is equivalent to doing nothing, i.e. the identity transformation. If we use I to denote the identity transformation, the identity of P is P for every point P in the plane. We can write this equivalently as follows. The rotation about D 120 degrees, rotating it again about D 120 degrees, and again about D 120 degrees, triangle ABC is equal to the identity triangle ABC. Continuing in this way, we see that rotating triangle ABC by 120 degrees 4 times in a row is the same as rotating it once by 120. Rotating it 5 times is the same as RD240, and so on. In fact, a whole number n rotated triangle ABC by 120 times n times in a row is equivalent to performing one of the following 3 transformations. You're either going to get rotation about D 120 degrees, 240 degrees, or the identity. Hence, by including identity transformation I in our list of rotational symmetries, we can write any number of rotations of triangle ABC by 120 degrees using only 3 transformations. For this reason, we include the identity transformation as a type of symmetry as well. So you could ask yourself, what if I rotated this thing 120 degrees 15 times? So then you would do this. You'd say, well, 120, 15 divided by 3, because there's 3 rotations that make 360, would be equal to 5 rotations. So that'd be equal to 5 360-degree rotations. So rotating it about D, let's see, what did I say, 15 times. Well, 360 times 15, let's think of it that way. Hey Siri, what's 360 times 15?
360 times 15 is 5,400.
So I could rotate D 5,400 degrees. And that would be equal to rotating it 360 degrees, because that was 15 rotations, and it would end up R of the identity I. So you would just say I. So you're either going to get R sub D 120, R sub D 240, or I. Only 3 things that will come out. That's all this whole page says. Okay, so page 4 brings us to an exercise. It says use the figure 1 to answer the questions below. 1, draw all lines of symmetry, locate the center of rotational symmetry. So I've already started this. So as you can see, I drew a circle centered about D, which has a radius greater than half of DC, but less than DC. And then I did the same, centered at C, radius greater than DC, greater than half of DC and less than all of DC, and then I drew a segment. So there is one line of symmetry. So I'll just pause and then show you the next one and so on. Okay, so there's a circle centered at A, circle centered at D, 2 points of intersection, draw a segment that is a perpendicular bisector to AD, and also BC since they're parallel. So all I had to do is do 2 of them, and I've got the 2, I have 2 lines of symmetry, but there's more. So let's keep going. So now if I draw a segment from vertex to vertex, okay, like so, that is a line of symmetry. And then if I draw from vertex to vertex, as so, there we go. Now all 4 of those intersect right there at the center. Those are all the lines of symmetry. Locate the center of rotational symmetry. So that's where those intersect. So that's going to be right about there. And then number 2 says, describe all symmetries explicitly. What kind are there? Okay, so there's line symmetry, obviously, because we drew 4 of them. A red, a green, and 2 blue. There's rotational symmetry. We can rotate it 90 degrees. We can rotate it 180 degrees. We can rotate it 270 degrees. And we can rotate it 360 degrees. So there's rotational symmetry, and the 360-degree rotation is the identity symmetry. C says, how many reflections are there? Okay, there are 4, 90 degrees, 180 degrees, 270 degrees, and 360 degrees of reflection. Not degrees of reflection. I meant 90 degrees is a reflection, 180 degrees is a reflection, a rotation of 270 is a reflection, and a rotation of 360 degrees is a reflection. Okay, I moved these in the wrong place. So what kinds are there? That goes there. How many are there? That goes there. And then finally, how many are reflections? And the answer is 4. Okay, number 3 says to prove that you have found all possible symmetries. How many places can vertex A be moved? How many places can vertex A be moved to by some symmetry of the square that you have identified? So where can A go? Rotate it, it can land on B. Rotate it, it can land on C. Rotate it again, it can land on D. Rotate again, it can land on A again. That's the identity. So by some specific symmetry is known as the image of A under that symmetry. Did you remember the identity symmetry? So it's 4. Vertex A can be moved to A, B, C, or D. Part B says, for a given symmetry, if you know the image of A, how many possibilities exist for the image of B? Okay, so the answer to that is 2. Part C says, verify that there is symmetry for all possible images of A and B. Okay, so then you would say, the point A comma B onto A comma B is the identity. AB onto AD is a reflection along AC. AB to DA is a rotation by 90 degrees, etc., etc., etc. D, using part B, count the number of possible images of A and B. This is the total number of symmetries of the square. Does your answer match up with the sum of the number from exercise 2, parts B and C? So the answer to that is 8. And part B we had 4. And part C we had 4, totaling 8. 4 rotations, 4 reflections, totaling 8. Relevant vocabulary is the regular polygon. A polygon is regular if all sides have equal length and all interior angles have equal measure. Okay, page 5 brings us to the end of lesson 15. Go to your problem set.